Georeferencing and reference coordinate system. Georeferencing. All the elements in a map layer have a specific geographic location and extent that enables them to be located on or near the Earth's surface. The ability to accurately describe the geographic locations is critical in both the mapping and GIS. This method is called the georeferencing. A spatial georeferencing system is required to handle the spatial information. Okay. The primary aim of reference system is to locate a feature on the Earth's surface or a 2D representation of this surface, such as map. A map portray accurately real world features that occur on the curved surface of the Earth. The objective of the georeferencing is to provide a rigid spatial framework by which the position of the real world features are measured, computed, recorded, analyzed in terms of length of a line, size of an area, and shape of a feature. What is a coordinate system? The coordinate system enables geographic datasets to use common locations for the integration. A coordinate system is a reference system used to represent the location of the geographic features, imaginary and observations such as GPS locations within a common geographic framework. Each coordinate system is defined by its measurement framework, which is either geographic, in which the spherical coordinates are lambda measured from the Earth center, or planimetric, in which the Earth coordinates are projected onto a two-dimensional planar surface. Unit of measurement, typically feet or meters for projected coordinate systems, or decimal, lambda degrees for latitude, longitude. The definition of a map projection for projected coordinate systems. Other measurement system properties such as spheroid of references, datum, lambda projection parameters like one or more standard parallels, a central meridian, and possible shifts in the x and y direction. Types of coordinate system. There are two common types of coordinate systems used in GIS. The global or spherical coordinate system, such as latitude and longitude, that are often referred to as a geographic coordinate system. Projected coordinate system based on a map projection such as transfer, Mercator, Albert, equal area, then Robinson, all of which along with the numerous other map projection models provide various mechanisms to project maps of Earth's spherical surface onto a two-dimensional Cartesian coordinate plane. Projected coordinate systems are sometimes referred to as a map projection. Geographic coordinate system. One method for describing the position of a geographic location on the Earth's surface is use spherical measures of latitude and longitude. Latitude, that means this, and longitude, that means this. There are measures of angles in degree from the center of the Earth to a point on the Earth's surface. This reference system is often referred to as a geographic coordinate system. They are measures of angles from center of the center of Earth है उससे कितना angle होता है from the center of the Earth to a point of Earth's surface. Okay, this reference system is often referred to as a geographic coordinate system, that is called GSC. A geographic coordinate system is a reference system for identifying the location on the Earth's surface of the Earth. A geographic coordinate system is a reference system for identifying the location on the curved surface of the Earth. Location on the Earth's surface are measured in angular units from the center of the Earth relative to two planes. The plane defined by the equator and the plane defined by the prime meridian which crosses Greenwich, England. Then a location is therefore defined by two values, a latitudinal value and a longitudinal value. Okay. The geographic coordinate system or GCS, geographic coordinate system or GCS consists of datum, prime and meridian and units. Latitude angles are measured in north-south direction. The equator is angle of OO. of a northern hemisphere has positive measure of latitude and southern hemisphere has negative measures of latitude. Longitude measures angles in an east-west direction. Longitude measures are traditionally based on the primary meridian, which is a imaginary line running from the North Pole through Greenwich, England to the South Pole. This angle is longitude. OO west of the prime meridian is often recorded as negative longitude. East is recorded as positive. That means इस डायरेक्शन में लॉन्गिट्यूड है, लॉन्गिट्यूड को दूसरा क्या बोल सकते हैं, डिपार्चर बोल सकते हैं. तो जो ईस्ट डायरेक्शन में उसको पॉजिटिव लेना है, वेस्ट डायरेक्शन में लॉन्गिट्यूड उसको नेगेटिव लेना है. देन नॉर्थ डायरेक्शन में लैटिट्यूड है उसको पॉजिटिव लेना है. देन साउथ डायरेक्शन में जो भी लैटिट्यूड है उसको नेगेटिव लेना है. प्रोजेक्टेड कोऑर्डिनेट सिस्टम, दैट इज रेक्टेंगुलर कोऑर्डिनेट सिस्टम. Surface of the earth is curved but maps are flat. Projected coordinate system is a reference system for identifying the locations, measuring features on a flat surface. It consists of lines that intersect at right angle, forming a grid. Projected coordinate system have an origin, an x-y axis, y-axis, and a y-axis, and a linear units of measure. Two-dimensional coordinate reference system is commonly defined by two axes at right angles to each other. They form a so-called xy plane. The horizontal axis is normally labeled x and vertical axis is normally labeled y. In three-dimensional coordinate system, another axis normally labeled z is added. It is also at right angle to x and y axis. The z-axis provides the third dimension of the space. Every point that is expressed in spherical coordinates can be expressed as x, y, z coordinate. टू-डायमेंशनल में एक्स वाई कोऑर्डिनेट एंड थ्री डायमेंशनल एक्स वाई जेड कोऑर्डिनेट इंडिकेट होता है. देन यूनिवर्सल ट्रावर्स Mercator, that is UTM coordinate reference system, has its origin on the equator at a specific longitude. Now the y values increase southward and x values increase towards the west. The UTM CRS is a global map projection. This means it is generally used all over the world. But the larger the area, for example South Africa, the more distortion of the angular conformity, distance, and the area curve. To avoid much distortion, the world is divided into 6 equal zones that are all 6 degrees with a longitude and latitude. Longitude from east to west, and the UTM zones are numbered 1 to 60 starting at the international date line. Zone 1 to 180 degree west longitude and progressing east back to the international date line. Zone 60 at 180 degree east longitude. The next one is surface modeling. In GIS, continuous surface such as terrain surface, elevation, temperature, then rainfall, pressure, population density, etc. are required to be modeled. Topographic surface model are referred to as a digital terrain model. A digital terrain model is a digital representation of the terrain features like elevation, slope, drainage, aspect, etc. Digital elevation model, digital height model, digital surface model are also widely used in different parts of the world to represent the various elements of the elevation. DTM is used in a generalized sense, and DTM normally represents elevation of the ground above a reference surface. DHM represents the height of the various objects like buildings, trees, etc. A good GIS software can integrate surface models into the spatial analysis. Various projects like flooding prediction, land erosion, sustainability, then mining potential, site selection, etc. are greatly enhanced by 3D modeling. Other layers of the information such as land cover, then hydrography can be overlaid on a topographic surface for the 3D. That means एक मैप है उसको वो उस पर दूसरा मैप इंटीग्रेट करेंगे तो आपको मोर इन्फॉर्मेशन मिलेगी. दैट इज इंफॉर्मेशन भी मिलेगी और 3D व्यू भी मिलेगा. For a 3D view of the landscape, digital aerial photos are also be overlaid on the surface model to obtain a more realistic view of a area. To model a surface accurately, it would be necessary to store an infinite number of the observations. Since this is impossible, a surface model approximates a continuous surface using a finite number of the observations. Thus, an appropriate number of the observations must be selected along with their geographic locations. The resolution of a DTM is determined by frequency of the observation used. Vector approach to DTM. Various models used in a vector approach to DTM are point model, lattice model, contour model, and TIN model. Point model. Multiple points are used to represent the surface. For example, a pyramid can be represented by a minimum of 5 points. 4 for base, 1 for peak. But in case of point model, the viewer requires imaging the surface joining the points, and hence it is not a good approach to represent the surfaces. The next one is a lattice model. Lattice is a representation of the surface using an array of equally spaced mesh points that are referenced to a common origin and has a constant sampling distances in a x and y directions. Each mesh point contains the z value at that location, which is reference to a common base z value such as sea level. Z values for the location between lattice mesh points can be joined by line segments. In lattice data model, each cell does not imply an area of constant value. In contrast, raster data model considers each cell as a square area with a constant value. Lattice is a representation of a surface using an array of equally spaced mesh points. Okay. Then contour model. Contour or isolines can be used to represent the surfaces, but the viewer requires to imagine the surface between two contour lines. TIN model. The triangulated irregular network stores GIS data for 3D surface model. In vector GIS, a TIN is used to create a DTM from either regular to irregular height data. The TIN method joins the height observation together with the straight lines to create a mosaic or irregular triangles. In a TIN model, the vertices of the triangles produced represent terrain features such as peaks, depression, and passes, and the edges represent the ridges, valleys. The surfaces of the individual triangle provide area, slope, orientation. These values can be stored as TIN attributes. Figure 3.26 shows a lattice model and TIN model. Raster approach to DTM, that is 3D representation of lattice and TIN model. Raster approach to DTM. In raster GIS, a DTM is simply a grid of height values in which each cell contains a single value representation of the height of the terrain that is covered by that cell. Conceptually, raster approach is ideal to represent the surfaces. How accurately the terrain can be modeled using raster approach depends on the complexity of the terrain surface and spacing of the grid. If the terrain is complex, for example, in a mountainous area like Himalaya ranges or the Western Ghats, a fine grid will be required to represent it with any degree of accuracy. If the terrain is relatively even, such as coastal area, fewer points will be needed to model it to the same degree of accuracy. Thus, the coarser resolution DTM may be used. DEM, that is digital elevation model. DEM represents a geographic grid of an area where the contents of each grid cell represents the height of the terrain in that cell. DEM consists of x, y, z coordinates. It is impossible to collect data from each and every point on the earth, and raster surface is generated by interpolating the available observations. This raster surface is known as DEM. For example, point data, contour, isoline, or even vector TIN can be interpolated to generate the raster surface. Photogrammetric techniques are used to generate the DEMs from remotely sensed images. A DEM is a representation of a topography of the Earth in digital raster format, that is, by coordinates of pixels, numerical description of the altitude. A DEM may or may not be accompanied by information such as slope, aspect, break lines, etc. about the ground cover. There is some difference between DEM and DTM. DEM includes only elevation of the data that are generally not considered as terrain surface. In most cases, DEM is grid data with elevation attributes which is suitable to use for analysis in raster GIS. The term DTM includes more general information than DEM. DTM is a model surface which contains also other data of the terrain such as peak points and ridge lines. Implementation of the GIS. In this age of the competitiveness, achieving increased efficiency through new technology is becoming a crucial organization. Implementation of GIS in this age of competitiveness, achieving increased efficiency through the new technology is becoming crucial. Organizations are looking for ways to improve productivity and increase profit through the automation. With the advent of affordable computer technologies, organizations have started to accommodate business functions through the use of desktop word processing, electronic spreadsheets, relational database, RDBMS technology, and computer-aided design and drafting CAD system to meet the challenges of the future. Corporate mantra is now increase efficiency and control cost. In order to achieve the goals, organizations are to reduce the duplication of effort, prevent redundancy, increase efficiency, and provide better services to their clients and community through the interdepartmental sharing and analysis of the common databases and resources. GIS helps to organize information in new ways, helps you to make new discoveries and get more out of the information you have. A GIS is an immensely powerful information management and computer mapping system. It links geographic location with information about them, so you can create maps, analyze information in new ways. Maps are graphic representation of the real world because most federal and state and local government policies, plans, and daily operations depends on accurate location-based information. GIS can play a vital role in making the governments more efficient and more productive, and often result in better service delivery. GIS has become an essential technology for government organizations in making better decisions, improvements in services, because most decisions they make are related to geography. The implementation of the GIS based information management system is often the first major opportunity to completely revamp and upgrade the record keeping, record management, reporting system of the organization. A successful GIS implementation requires strict adherence to a time-proven technological task tabs. The results, outputs of one task is the input to the next task. Though some of the tasks can be treated as independent, as 90% of the tasks are interdependent. The sequence of the events should be: conduct a requirement analysis, develop a pilot project as proof of concept, design logical and physical databases for the land base, develop the mapping significance, acquire a quality-based map, set up GIS organization, acquire hardware and software, and train personnel, develop the database design to support the identify applications, develop application from the priorities, prioritized list identified in the requirement analysis documents, develop procedures and standards for data conversion, convert data to support the application being developed, develop data maintenance policies and procedures, develop application for the other users and increase the user base over time, implement a fully integrated system comprising all the departments within the organization or institution, incorporating the program developed in the previous phases. GIS team may include the personnel from various levels. GIS team and the roles are as under GIS project manager, that is planning implementation of GIS application, planning of GIS products, selection of hardware and software, consultation with the users, management of the personally, then budgets and fundraising, etc. Then database manager, design of GIS database, maintaining and updating of the database, production of GIS database, quality control of the geospatial data, plan of the data acquisition. Digital map maker, compiling of the existing map sources, map digitizer, attribute data input, data acquisition with the aerial photogrammetry and remote sensing, design and production of the digital map. System operator, operation of the hardware, software, other peripherals, management of the materials, backup of the program, data files, support to users' requests, etc. The next one is programmer, programming for the data conversation, then programming for the application software, solution to problem with respect to the data and program files, SPITE analysis, develop SPITE analyst, that is developing application, training to the digital map maker, analysis of the GIS. Okay, thank you.